Right. So good morning, everyone. So welcome, Andy. And today we have online classroom for open platform. And for the fourth class, okay. So let me switch my slides. David. Okay. So let's start with this presentation. So next slide, please. Okay. So this is the arrangement for today. We will have, as usual, two sessions. First hour and the second hour. The first hour we'll talk about RGB-D sensing. So in order to do visual perception or robot vision system, first we need to get the data from the sensor. And over here today we talk about two types of sensors, sensor data. So the first type is the RGB, which is the images, so same like camera. And the second type of data is depth sensor. So it's the distance between the sensor and the object. And we have it in 3D, so we can have the 3D model of the object in front of the robots. So with these two kind of sensors, we can later on do some processing with some algorithm, which is mainly I will talk about image processing in the second half of this presentation, to show you how the robot or the system able to perceive or to understand what happened or what are the objects, human, that appear in the environment. Right. So this is the arrangement for today. So the first half and second half. And as usual, this video will be recorded. So please be careful on your privacy. And we are now live on Facebook. Right. So as a reminder, I would like to call everyone to please sign up for the competition, especially because we have a lot of competition-specific information will be assimilated through the registration. So which means we will contact the team leader to give more detail about the competition, the schedule, the preparation, and so on. So please sign up, although you might still consider to take part or not while joining this class, but I would like to encourage you to sign up first so that we can, so that you will get more information about the competition. Right, so let's get started. So next slide, please. Okay. So last week we discussed about speech interaction. So inside there we have speech synthesis, where we're able to make the robot able to say something according to the text that you input, and also the robot able to recognize what the human said or what the user said. So with these two parts combined, we actually can develop the speech interaction system for the robots. So which means this is a very important fundamental for service robot, because we need this interface for the robot to able to interact with normal user, because service robot is meant to be operate in domestic or normal environment where we need the interaction with the public or normal people in order to serve or do some operation in order to create the value in the domestic environment. So with this fundamental, so we will continue today to introduce you some function in vision system. And later on, I will introduce you the assignment for today, which is the combination between these two. That's why, as a prerequisite for this class, you might need to have know the development of last class for the speech interaction. So that will actually become the base of the system. And eventually we can combine with the vision system, and you can have a very interactive vision system for the robot system, or even how to say, an AI intelligence system that you can develop for practical application. Okay, so that is the previous assignment and also the prerequisite for today. Right, so next slide. Okay, as usual, for this class, we design totally based on the materials you can find within your house. Okay, so for today also, although we are using actual hardware for development, but this hardware is very common that you can easily obtain in your house, I suppose. Right. So for the hardware, we need a webcam, which is, I think, is very common, because I think almost all modern laptops come with built-in webcam, so that is not a big problem. But just in case that your webcam is not working or you don't have one on your laptop, so you can easily obtain the USB, external one, right? So you can get one which is cheaply available everywhere. So you can get one webcam and just start via USB to your laptop, and it should work with our program and software. Okay. And optionally, if you somehow have done some development, you have RGB-D sensor. For example, you get the sensors from Xbox, Xbox 360. So this RGB-D sensor can be used for today's development, right? So just in case you have any other types like Intel or anything, RealSense or Asus Action Pro and so on, I can name a lot. And over here, the example that we use is we're using the OBEC Astra, but almost all these sensors use the same technique and algorithm. The only difference is maybe it's the driver. So you need to install the appropriate driver, especially over here we are using the ROS system. So if you have the driver or it is a very well-known sensor, you can easily get the sensor's ROS driver. Okay, so you just need to install that, and the rest of the development is the workflow will look very similar. And lastly, what you need is a laptop computer, which is as usual, we have the computer that you use for your development. And for the software side, we are using Ubuntu system, ROS system, and later on I'll introduce to use all the component software that you need. But if you are using the VirtualBox image from Jupyter Robot, you will have all those software ready for you within the image itself. Okay, so that's all the things that you need to follow this class. So I guess everyone should able to gather all these things, even though you are working from home. Okay, next slide. Okay, so first, let me introduce you a little bit about robot vision system. So the vision system that we use for robotics, especially mobile robots, are a bit different from computer science and from other disciplinary. We start from, okay, I will start the story from mobile robots. So we know mobile robot is a very matured robotics field after the industrial robots, the industrial robot arm. So when mobile robots start to develop visual perception, usually the sensor will be laser rangefinder. Okay, so we use a lot of laser rangefinder in mobile robots as a start, and then later on this distance-based sensor expand to like 3D, 2D, and then we're using laser and also ultrasonic and infrared and other things. So all these optical sensors with the purpose to measure the distance. So when you go to 2D and 3D, so we can do the mapping, which is very important, the navigation module for mobile robots, right? Then later on, we add in, okay, so not just to measure the distance using optics, using optics as a sensing method, we also add in cameras, which is we start to collect the color information. So with the RGB sensor, with color cameras and so on added in, so we can use that as, for example, in visual SLAM, for example, they are using images in order for navigation. But later on, as we transition from mobile robots to service robot, we require more information about the environment. For example, not just we want to do the navigation, we also want to detect object. For example, okay, in navigation, you want to avoid certain obstacles, you want to detect human, you want to detect objects, and so on. So we use color cameras to get the images and use the technique from computer science, which is the image processing, to understand the object and also to understand what happened to the environment. So, and later on in almost very recent, which is a new breakthrough, which is the RGB-D camera or RGB-D sensor. Okay, that is a combination between the distance sensor and also the color camera. So you can see I show you an example, which is a Microsoft Xbox Kinect Xbox 360 Kinect sensor. Right, so that is actually a breakthrough, is because not the technique itself, because to combine visual and distance sensor data, it have been a lot of work about that before this. But what breakthrough is like Microsoft actually packaged this sensor into a very compact form, which is a very small and a very handy, very portable, and the price is very low because it is designed for gaming machine, which is the Xbox. In order to track the movement of the human, okay, for them to design games, for example, the dancing games and so on. So this breakthrough actually make these sensors become very affordable and very available for robotics community in order to leverage this sensor and this technology for various types of robotics application. Right, so I'll go to next slide to explain to you in more detail. Okay, so we use a lot of these RGB-D sensors in our development over here for our mobile robots because a few reasons. First, it's like it is very versatile, very portable, and also the price range is very low. So we can actually attach more than one on our robots for various applications, and it can be used for navigation, for human perception, and so on. So it can use for face recognition, it can use for a lot of detection. Okay, in terms of using a visual technique. So as a brief introduction, I'll show you some specification on the slide. You can see it is RGB-D color, VGA video camera, plus a depth sensor, which is composed of an infrared projector. So you can imagine it is like a projector, right? The projector that you use to project slide, a projector, but the lights coming out is infrared. So it's something that not visible for your eye, but it's visible even at night. So for example, if you're using this sensor, you off your light and everything, it still works, okay, because it projects out infrared lights, and then it have a monochrome CMOS sensors to as a receiver. So you receive all this infrared projection that bounce back from the object and the time of flight. Okay, later on I'll explain about this to get the distance. Right, and the resolution is about 640 times 480, which is optimal value for our processing because we can't really go for very high definition because it will actually bring a lot of computing requirement to your machine. And of course, it's written there about 30 frame per second, but usually our requirement for service robot application is about 10 frame per second is sufficient. For example, you want to do gesture recognition and so on. Okay, and have a look on the sensor range. You can see over there, the blue color indicate the optimal sensing range, which is you can see from the sensor, it is actually 1.2 meters to 3.5 meters is the optimal, more effective range, which is very comfortable for service robot. Although initially this distance is designed for the user to stand in front of the television for the computer game, but this distance is really very suitable for service robot because that is the comfortable distance for interaction between normal user and service robot. For example, like when you want to talk to robots for some interaction, for example, like you want to do it in a reception hall or you want to do it in a domestic helper scenario. So this distance is very comfortable for human to interact with the robot. So with this distance range, this sensor is very suitable for our development. That's why in this class we recommend these sensors for our development. Okay, right, next. Okay, so very brief introduction about the sensing theory. Okay, right. So the concept of how the distance is being sent is we're using the time of flight (TOF), which is the distance of the object to the sensor. And then how we measure is okay. So you imagine we have a transmitter, which is we project the light from the sensor. Then the light will bounce back from the object. So that is the optic, the fundamental optics. With that, you can see the object itself because it actually bounces back from the object itself. And whatever that's bounce back represent the color. So you can see the object, our eyes see the object based on this concept. So similarly, we're using this natural phenomena of optical phenomena. So we use a light medium. We send the lights from the transmitter to the object and it bounces back, and then we have the receiver. So the difference of the time for this whole process, we measure the time, right? So this is the time of flight, and then we divide by 2 because the distance traveled is double of the distance that we want. We distance is 2 and back, so we have this 2. So we divide by 2 is basically we can get the distance between the two, the sensor and the object that we want. So with this very simple concept, we're able to measure the distance using optics. Right, next concept. Okay, so we know how to measure the distance. So how the color sensor works. So for color sensing, we use a basic component called photodiode, which is some element that can convert from light intensity to electrical signal. So if the light is very dense, which is very bright, then you will get higher signals and so on, right? So it depends on how bright or how intense is the light, and the photodiode will give you the equivalent electric signal. So we're using this basic concept. Then we arrange this photodiode into an array, right? So just like what you can see on the diagram, on the figure in top right hand side. So we arrange the photodiode into an array. Then we pointed a light source onto the array. So that array basically is a very similar structure within a CCD or a CMOS sensor. Okay, so this CCD and CMOS sensor are very similar. It's just that the architecture is a bit different in terms of all the sensing process, but it works with a very similar concept. Okay, so we have this CCD or CMOS sensor as our color sensor sensing device. So we catch all the light, and then we try to measure the light intensity of each point. So over here, each point, we call it a pixel, right? So we use a photodiode, we measure it. So okay, so maybe you're familiar, like when you want to buy a digital camera, so you look at the megapixel. So the megapixel is the number of this photodiode in one sensor. Okay, so that's why the more sensors, the more pixel you have, I mean like the number of pixel you have, the more sharp the image you can get, because you can get a very tiny difference between two dots, okay, right, to compose your image, right? So with that, we can get the intensity, which is the light intensity. But how about the color? Okay, so between the sensor and also the lights, we actually have one color filter. Okay, so this color filter, it has certain pattern that it arrange this RGB filter. Okay, so you can see I show you one example over there. So that is one arrangement, but we have various kind of arrangement for this. So RGB color filter, and with this color filter, each color filter will give you the value of the respective intensity of the color. For example, how intense is the red component in that light, or how intense is the green color and blue color, and so on. So for the red, green, and blue, so it will filter out the other color, and then it will tell you how much value is the pixel in terms of pixel value for the particular photodiode. Okay, so with that, for the pixel value, usually we'll measure between 0 to 255. So you have 256 level to measure the intensity. So that's why our RGB value is between 0 to 255 for this tree. Okay, so with that, we convert. So you can imagine when we use this sensor to catch the light, we can have a big array of a lot of dots. Okay, so you can imagine like each dot have a value of R, 0 to 255, G and B value of 0 to 255. So it's very similar like X, Y, Z. So, but in over here, each dot we have RGB value. Okay, so with this arrangement, we can get a very big array to represent the whole picture, and each dot will give you three value, which is the R, G, and B value. Okay, so with that, we can represent the picture in front of you in terms of all this pixel value. Okay, so that is how the color sensor obtain the lights and convert it into a digital number that represent your image. Okay, so that is the concept. Right, next. Okay, so once we have the value, okay, we have the numbers that represent the light or the composition of the light, which is the image that represent what the actual scene look like. Okay, so once we have that, we can use a lot of computer algorithm, mathematical algorithm, to do digital image processing. So digital image processing is a process that once we got the data, we use some algorithm to do some analysis and processing in order to achieve certain functionality. For example, classification. So we can classify colors. For example, on this particular image, what are the colors and what is the distribution of certain color, for example, like red color and so on. So we can do a lot of classification. We can even classify objects and so on based on certain features. Okay. So the next one is feature extraction. So we can get, for example, the edges, for example, the eye, for example, different features that we can actually analyze from the distribution of the value. Okay, so based on the value, we can actually do some mathematical calculation and get certain features based on the number. And so on. We can do a lot like multi-scale signal analysis and pattern recognition. Okay, so we use a lot of pattern recognition in terms of recognition. For example, to detect handwriting, number plate, and character, alphabet, and so on. So pattern recognition and projection. Right. So we have a lot. Like the list is a lot, and this digital image processing is a big domain that I cannot finish explain in just one slide, but it's for you to explore. So what we can do after that. But for this class, we will show you how we use this thing in service robot. Okay, next. Next slide, please. Okay, so before we start, let me introduce to you the challenges that or the development that we aim in service robot. Okay, so because we want to show you the difference between the challenges in service robot development in terms of this visual perception as compared to the one in computer science. Okay, so it might give you a little bit different, especially we are more, how to say, application based. Okay, application oriented. So we develop our application, our visual perception application based on the challenges or based on certain objectives that we want to achieve when we develop service robot. So over here, I'm taking this RoboCup at home scenario to explain to you what are the R&D, research and development aim in the perspective of visual perception development. Okay, so first we look at the photo at the right hand side. So that is a typical competition area. So you can see it is very similar like a normal household environment. Okay, so we have a living room, we have various kind of dining room, kitchen, and so on. And then inside this environment, we have the actual furniture, the actual flooring. We have people that is working inside. We have object. You can see plant. You can see our objects on the table and so on. And then we have a normal lighting, like we have the lightings up there. So we can see uneven lightings. We have a lot of shadow. We have a lot of people and things are running around. So it is a very noisy and complicated environment for vision system. Okay, so because in vision system, important is like we need to have a very clean background. But over here, we don't have a big, very clean background. So all the backgrounds will give you like a very noisy background with all the objects and also different lighting condition. Okay, in different corner of your house, different perspective, and also it is a 3D environment. So depends on the height of the robots and where you place the sensor, and also the sensor or the robot is actually moving inside this environment. So your sensor is actually maybe vibrating and in different angle, different orientation when you look at a certain object that you want. For example, you ask the robot to enter this room and to find some person, right? And then you don't know this person, is it taller than the robot or is actually sitting down or is lying on the floor and so on. So we have various angles, we have various orientation, we have various lighting condition, we have various and very noisy environment, very noisy background. So that are all the challenges that we will face when we want to develop vision system for our service robot. Okay, so those are the things that you can imagine, and please put this thing in your mind when we develop the application, because we cannot develop an application without considering all these factors. If you don't do that, when you want to put your application on actual robot for the operation, then you'll find a lot of problems. You'll find like, okay, for example, one of the research that I work in my labs is like the lighting condition. So in a room, for example, we want to grab something. So the object, okay, so the objects that we concern, you can refer to the picture photo on the right hand side, the B, typical object. So you can see for service robot, we need to identify a lot of objects, household objects. And inside there, we have like snack, drinks, food, and household item, a lot of different kind of household item, bottle, all the furnitures and all the tableware, for example, all the TV remote and so on. Also, all these things, it comes with various color. The label is very colorful. The shapes and size and weight and everything are very, very different. Okay, right. So in order to identify all these things, you can see like when the thing put in cabinet, put on the table or under the table, they actually have different light intensity and it looks very different. Okay, so later on, I think David will show you like how this color, if let's say we use the color, to detect how this color is greatly affected by the lighting condition. So for example, we switch on the light, or we switch off the light, or we have not dimmed the light, and so on. The color information is it can give you very different value. So how we want to make our application or our algorithm in terms of vision in order to do all this detection, that is the challenges in our service robot visual perception development. Okay, so I hope you grasp the idea that what are the R&D things that we can do. So let's proceed to the next slide. Okay, so in practical, so what kind of tasks? Okay, so I'm just showing some example and show you what is the standard benchmark that usually we have in our competition. So over here, I want to show you two typical tasks that we have in our rulebook. Okay, but this rulebook is for 2018-2019 rulebook. So we have one task called speech and person recognition, another task called sorting grocery. Right. So this one is within the rulebooks of RoboCup at home. And inside there, for example, like speech and person recognition, so the robot need to like talk to a number of people, and then these people will actually gather in front of the robots and ask the robot to identify. So on the left-hand side, you can see a pictures with several people, and inside there, okay, the green one represents the operator, which is the person that interacts with the robot. So which means the robot actually know this person beforehand. But for the rest, the robot actually have no idea who are they. They just come in during the competition and expect the robot to identify them. So which means you need to recognize their faces. You even need to know what is their gender. For example, over here is a lady or man or boy and so on. So you need to know all these things. So with a very conventional pattern matching and techniques, you are not able to do this job. You need to like have more modern face recognition, which is you have like deep learning based face recognition that you analyze the features of the face in order for you to detect faces that is not within your database. And also you need certain features in order for you to recognize whether it's a female or male, right? And also you need some recognition features because you need to identify if this person is someone that you know within your database or not. So these are the standard that we require in this competition. And then not just also to identify object, I mean to detect object, you also need to understand some nature or some features of the object. For example, in sorting grocery, we need to arrange things that belongs to the same category. So for example, like when we want to sort out the things, the grocery, and put it on the cabinet, so we can refer to the right hand side image. So over there, when we want to arrange all these things, so we need to identify, first we need to detect the object, then we need to recognize what object is that, then also we need to understand the relationship between this object with the other object. For example, like we want to arrange all the drinks together. So you need to understand a can of Coke, and also the milk represent the same category in terms of it's a drink. Okay. Then of course, like if you want to sort all the fruits together, you need to know like banana, apple, pear, they belongs to the same category. Okay, so over here, so it is not just to understand the shape, the colors, and so on, but you need to understand the meaning of the object as well. So these are all the challenges in our visual perception development in at home. So these are the aim and the things that we can learn in our development. Right, so next. Okay, so let's start some exercise. Before I start the exercise, okay, while you get ready your PC system, we start with robot vision with ROS. So we want to start our development within the ROS framework. First, let me introduce to you the driver that we use in order to drive our sensor. So over here we use OpenNI 2, which is OpenNI is the first ever open source driver for Kinect sensor. And then later on we have this OpenKinect, which is after the OpenNI 1 become not available, then we have OpenKinect, and then later on OpenKinect 2 appear. But eventually, these are the two reference that we use for as a driver for our RGB-D sensor. Okay? But there are a lot more, but these are the tools that we use in our development. Okay, so we can refer to that. Then we have a library, which is this point cloud library. So this point cloud library is a tool, a library to help us to process the raw data from the distant data from the sensor. So it will process the data, and then eventually we'll get a very nice, we filter out all the noise, and we very nice structured distant 3D distant data in a point cloud format. So we can see later on, David will show you later on in RBs to show you how this point cloud look like. Okay, so the sensor, how it looks like. Okay. Then after that, we have the application library, which is the OpenCV. So OpenCV is a very well-known open source library for computer vision. So it provides a lot of algorithm and application example. Even like all the source code are free and open. So you can do a lot of computer vision development with all the tools and also all the example that is provided by this OpenCV library. But of course, OpenCV is not that it can't be directly used in ROS because, for example, the way how ROS handle the data and the way how OpenCV handle the data might different. They have maybe a different convention in terms of coordinate system, in terms of the data structure, and so on. So in order for this class, because we aim for a beginner to learn this thing, so it is not easy. For example, like if we show you how to start OpenCV development in ROS from scratch, so it is really not easy. So for that, we introduce one very nice example that is developed by the ROS community. So in ROS community, we have one group of people that work on robot perception, which is all the sensing data and so on. So inside there, this group of people actually develop this OpenCV apps. Okay, you can go to the website over there and see. But I recommend you to go to the OpenCV one website to see the algorithm, because later on you will use a lot of different, for example, the cam shift. Later on you will have the face recognition, which is use the cascaded filter and so on. So if you want to know all those algorithm, please head to the OpenCV website to find the equivalent explanation. They have a very in-depth technical discussion explanation there, and they even like explain to you almost like line by line of the example. Okay, so we can find the information there. But over here, we are using the OpenCV apps, which is developed by one ROS community, and you can go to the website to see the list of examples that are available within this library. Within this library today, we are going to show you a few, right? We are going to show you a few that we feel that is related to our development in service robot development. Okay, but of course you can explore more if you're interested for more computer vision application and so on. So you can head to and see the list of examples that is available over there. So you can get more information there. So I list down all these references that you can study after this class. Okay. So first we start with installation, but of course, if you are using the VirtualBox image from Jupyter, everything already like installed and set up nicely for you. But in order for you to know what are the tools that you're using, so let me give you some brief explanation. So first is that the Astra setup. That is actually the setup for our sensor, RGB-D sensor. So if you're using other different type of sensor, so for example, most of you will be using the USB camera. So that is the driver that available within ROS kinetic version, the ROS kinetic USB cam. So that is the driver that you need in order to drive the USB camera. This driver will run almost 80 to 90% of the USB camera in the market. That's what I can say, but not all, because maybe you will have a very specific, very special USB camera that come with a very different driver, or even you don't work with Linux, then you might need extra effort to find the driver. Okay, but that one, we will leave it later on. If you have this case, you can discuss with us later on. But in general cases, this driver should work with you. So make sure, later on, David will guide you through how to check and make sure that your USB can work with your system. Okay, then the next step is how to install this OpenCV apps. Right, you can see the same thing. We head to our Catkin workspace, then we clone the source code, the example source code, and then we make it. Okay, we compile it, and then we can use it. Later on, David also will show you where is this example, because like you might want to refer to the source code of the example in order for you to do your development. Okay, later on we will tell you more information about that in the demonstration. Then lastly, multiple Astra sensor. This is one of the case that I show you how we can run multiple sensor. So for example, in Jupyter Robot, we have two Astra sensor. So how we want to arrange these two sensor and run it simultaneously, because we need them to run simultaneously, one for navigation and one for the human perception. So how we actually put them, run it, and then we need to make sure that they actually go to a different topic name, because if we have the same topic name, then we'll have conflict. So we want to like arrange them and arrange them in such a way that we can manage both together. So if later on you want to use two webcam or two different sensors that you want to put it together, so this will be one of the reference to show you how you can run multiple sensors together. Okay, but of course it's not directly can apply, but we can give you some information for your reference. Okay, next. Okay, so I tell you the basic workflow, and later on David will explain to you and demonstrate to you how to do this. So in order to start for the first half, what we need to do now is to first bring up, which is to start your sensor. So once we start the sensor will start to get the information from outside, and then it will process it and push all this information in appropriate order, which is if it is a raw image data, then it will put in equivalent RAW topic and depth data and so on. So we need to have all these things ready. So in order for all these topics ready, so first we need to bring up. Then after you bring up, we will show you the way how you can examine all these things by displaying the data in a appropriate form. So we have the data, but we don't want to see the data in figure, okay? Because you can't understand the figure. For example, I tell you the RGB value, you can't actually imagine it in a image form. So we have tools in RAW that we use this image view in order for you to see how is it look like in a picture form, and also the depth data, and also later on David can also show you in RViz to show you how this data look like in a 3D form. Right, so I'll pass this to David and you can start demonstrating this idea.
Okay, thank you, Professor Jeffrey. Before we use the USB camera on the in the Jupyter robot VirtualBox system, we need to mount the device to the VirtualBox. First, we need to check whether we have the USB camera. For me, for now, I use this computer as I plugged two more USB camera to the computer. So if we click the device menu, we can choose the USB or the webcams. There is some difference between the USB and the webcams. First is the webcam is a camera, especially the built-in camera. For example, my computer is a notebook. My notebook is a Xiaomi. So we have a name of Xiaomi USB 2.0 web camera. If we click here, I can directly connect the web camera of the notebook to the VirtualBox. But we also can use another way to choose the camera from the USB device list. And because I use a Logitech web camera and for demonstration, so I will use this one, Logitech web camera. Just click the name of the camera. The double check, we can find the camera have been mounted to the VirtualBox, and it will not show from the web cameras. So for your notebook, I suggest you check both of these methods. First, you can use the built-in camera with the webcams. And if it doesn't work well, you can use USB cam from the, you can use USB method from the USB camera list. For example, this is also a USB cam list name in here, Xiaomi USB 2.0 web cameras. So it's also okay. So if you have problem, then change to another method of connection. And first time you bring up the camera. We have the package name USB cam and the launch file. The program will automatically open a window to show the image from the web camera. So this is a sample for the example for the demonstration of the color satisfaction. So I just show you what we can see from the camera, and we have we also set up an environment to make some tests about the effection of the light condition to the image processing. So I will show you our environment. Just wait a moment. OK，你进设好，你进那个设计，对你出来就好。So this is the environment what we have used for the demonstration. This one is a USB camera. I use a long wire to connect with my notebook, and this is a table with several objects on the table. So we can get the picture from the USB cam to see what happened in the color segmentation. And this is our Jupyter robot, and we will do some demonstration to show how the RGB-D camera look like. Okay. And Jeffrey, do you need me to show some depth image?
Yes, please.
Okay. For the RGB-D camera, I have to use a real robot to show the RGB-D result. So first, I need to connect with my robot, and this window is a TeamViewer software connection from my notebook to the real robot. Just look, as I show you on the in the office room. So I will use the following command to show you the result of the RGB-D image. 开电。This is only can be done on my on the Jupyter robot because we have some config about the multi-astral camera. This command is to bring up the robot. This command is used to bring up the 3D sensor, and we show the and we use the RVs to show the result what we can see. RVs is a very useful software for the data visualization in ROS. So we can see there is a robot here, and we can change the position of the robot, and I get the real image from the RGB-D camera. So you can see the camera get some image from the RGB-D camera here, and we can see there is a sofa here and some boards here. But what is the real image from the camera? We can use this one to show the normal image. Okay, the normal image. This is a and by topic. Drag the window out of the menu, and we can enlarge. Okay. This is the RGB image, and this is depth cloud image. Depth cloud image here. Okay, the color will show you the distance from the robot, if the object is near the robot, the color will be more red, and the color will be more green or blue if the object far away from the robot. So we change the angle of view. We change the change the view of the robot to show you the change of the image. We can see the sofa here. Sofa here, the board here. Yes, this is the result of the depth camera. Okay, Jeffrey.
Okay, right. Thank you, David. Thank you for the demonstration. So we appreciate a lot. So this is done in collaboration with Jupyter Robot. So just now you saw the actual working environment in Jupyter Robot, and yeah. But of course, you might not able to test this at home because you may don't have the 3D sensor. But at least all the process that using the color sensor, that is something that we can do with the webcam that we have at home. Right. So with this, we able to bring up the sensor with all the drivers. Then after that, we can get the sensor data, which is proven when you able to see the images from the sensor, which is the color images and also the depth images. So with that, we have completed the first half of this presentation, which is we able to acquire the sensor data from the RGB-D sensor. Okay, so we will take a break about 5 minutes to let you test. We will turn on the group chat. We will start to interact with you in the group chat. So please tell us if you can see images or you face any problem, right? So please post up if you have any question to ask. Use the group chat, show us your problem, and we will try to help you. Okay, so we will take a break for about 5 to 10 minutes. Okay, it depends on the condition of if you have problem or not. Then later on, we will proceed to the next half, which is we will show you. So once we have all this data, so what we can do with the data in order to create some application, right? So we will take a break now. So now it's about 10:02. So we will break from 10:02 to about until like 10 minutes later on. Okay. So within this time, I hope you can test your camera with you and tell us if you're able to see the images from your webcam. Okay, right. So thanks, and we will come back again in 10 minutes later, which is 11:10. Right. So we come back like 7 minutes later. Okay. So please try and tell us like whether you get the images or not. Okay. Thank you, and please communicate with us in the Q&A.